thinking atoms, the universe waking up. Consider, for a moment, the hand you might be resting on your chin right now. It is composed of carbon, hydrogen, oxygen, nitrogen, and a sprinkling of heavier elements like iron and calcium. These are dead, inanimate ingredients. On their own, they have no desires, no memories, and no capacity for wonder, and yet, arranged in a specific, breathtakingly complex architecture. Those same atoms are currently reading this sentence, processing abstract concepts, and feeling the weight of existence. It's like the alphabet. Separately, letters are interesting, but far less so than when put together in a masterpiece of literature. If you were to take a magnifying glass and study the letter T in a copy of Hamlet, you would never find tragedy or melancholy inside the ink of that single letter. Those feelings aren't in the letters. They emerge only when the letters are arranged in a specific, highly organized sequence. A single carbon atom isn't alive, black, or hard. But arranged one way, carbon emerges as soft pencil lead. Arranged another, it emerges as a diamond. Arranged with other letters, oxygen, hydrogen, nitrogen, it emerges as you. Similarly, a single neuron isn't conscious, it just fires electrical signals. But when you put 86 billion of them together in a precisely specific, sophisticated network, suddenly you have self-awareness. This is the great paradox and the supreme beauty of our reality. We are the universe getting to know itself. The fact that we even know we are made of atoms is a miracle of deduction. For most of human history, matter was a mystery. It wasn't until the last few centuries that the thinking atoms of the human brain began to systematically dismantle the mystery of their own construction. We discovered that elements combine in specific ratios, and eventually we peered into the heart of matter to find it was mostly empty space. In ancient Greece, Democritus proposed that if you kept cutting an object in half, you would eventually reach a particle so small it was uncuttable, or atomos. Later, the Roman poet Lucretius preserved these ideas in De Rerum Natura, on the nature of things. He suggested that just as different words are formed from the same letters, the entire universe is formed from the same basic atoms in different arrangements. They had no way to prove it. For 2 millennia, the Aristotelian view that everything was made of 4 continuous elements, earth, air, fire, water, ruled supreme. Fast forward to the late 19th century. Ludwig Boltzmann championed the idea that gases were made of individual atoms and molecules in constant motion. Boltzmann didn't discover atoms under a microscope. He deduced them because he realized the math of the visible world didn't make sense unless the invisible world was made of tiny colliding billiard balls. Boltzmann's genius was realizing that the laws of nature aren't ironclad commands handed down from above. They are simply statistical certainties. In the 1800s, scientists knew heat was a form of energy, but they treated it like a fluid called caloric that flowed from hot to cold. Boltzmann found this explanation lazy. He looked at a piston filled with steam and asked, "What is actually happening here?" He realized that if you assume the gas is made of billions of individual atoms, heat isn't a fluid, it's motion. In hot gas, atoms are screaming around at high speeds. In cold gas, atoms are sluggish and slow. Boltzmann couldn't track every single atom. The numbers were too high. So he applied the math of gambling and probability to physics. Why does heat move from a hot object to a cold one? We imagine a force pushing it, but the reality is simpler. It is statistically overwhelmed. In a hot object, energy is clumped together, a highly specific, low probability state. Once that object touches something cold, the energy begins to jitter and spread. There are trillions of ways for energy to be spread out, disorder. and only one way for it to stay clumped: order. Nature doesn't hate order. It's just that disorder has more ways to happen. This realization was the definitive proof for the atom. If matter were a continuous smooth fluid, as Boltzmann's rivals believed, the concept of arrangements would be meaningless. You can't rearrange a smooth liquid into different patterns at a microscopic level if there are no parts to move. By proving that entropy is a count of possible arrangements, Boltzmann made atoms a mathematical necessity. You cannot have a count if you don't have things to count. According to the second law of thermodynamics, entropy in an isolated system always increases. Things naturally move from a state of neatness to a state of mess. If you have a box of alphabet tiles arranged to spell a poem, low entropy, and you shake the box, the letters will inevitably scramble into gibberish, high entropy. There is only one specific way to arrange the letters to create that masterpiece. There are quadrillions of ways to arrange them into nonsense. Therefore, probability dictates that chaos wins. In scientific terms, disorder is simply more probable than order. Consider a deck of cards. There is only one specific sequence that is perfectly ordered by suit and rank, but there is an unimaginably high number of ways for the deck to be disordered. Maintaining order requires a constant work or energy input. The moment an organism stops consuming energy to maintain its internal order, it succumbs to entropy, death, and decay. Order is valuable because it represents a low probability state that requires effort to sustain against the universal tide of chaos. Because order is rare and essential for life, our brains have evolved to be hypersensitive pattern recognition machines. For our ancestors, spotting order in a chaotic forest, the symmetry of a predator's face, or the repeating pattern of a beehive was the difference between life and death. When we see a disorder where there should be order, a messy hospital, a glitching computer, or fractured logic, we feel uncanny, immediate stress. This is an evolutionary alarm bell warning us that the system sustaining us is failing. Conversely, we find symmetry and rhythm beautiful precisely because they are rare. Art and music are human attempts to impose a temporary, local order on a chaotic world. The price of order is eternal vigilance. In biological terms, this is literally true. Our cells spend most of their energy just preventing themselves from falling apart into chemical equilibrium disorder. Entropy is also a crucial concept in science because it defines the arrow of time. The universe moves in one direction, from order to chaos, not because it's being pushed, but because it's stumbling into the most likely state. Entropy is also the first rule of psychology. It is difficult to build a reputation, but very easy to ruin it. Every jackass can kick down the barn, but it takes architects to build it. The world is skewed toward the negative. We feel a loss much more strongly than an equivalent gain. To lose a house is much more painful than to buy a second one. There are a million ways for a body to be broken, disorder, but only a few ways for it to be healthy, order. We inhabit a reality defined by a cruel asymmetry. There are a million ways for a body to break, but only a handful of ways for it to be whole. If there is a cosmic architect behind this design, we must judge them by the blueprint they provided. A creator who establishes disorder as the effortless default state, with the maximum entropy of the whole universe, heat, death, as the inevitable end of all things, cannot be called good by any human standard. Such a designer is either a cosmic nihilist or an architect of planned obsolescence. Because broken is a much more likely state than healthy, Our brains are wired to be hypersensitive to any sign of decline. We don't notice when our heart is beating perfectly, but we notice the second it skips a beat. We humans are the rare, fleeting arrangements that haven't scrambled yet. We are the masterpiece written in the margin of a book that is slowly being shredded by the wind. Going back to Boltzmann and his concept of atoms, the scientific establishment of the late 19th century, powerfully led by Ernst Mach and Wilhelm Ostwald, wasn't just skeptical. They were hostile to Boltzmann's ideas about atoms. They adhered to a philosophy called positivism. Since no one had ever seen an atom, Boltzmann's models were dismissed as metaphysical hallucinations or mathematical fictions. Feeling isolated, mocked, and suffering from declining mental health, the giant of science, Boltzmann, took his own life in 1906. Ironically, the empirical proof Boltzmann needed arrived just a year before his death, but it took time to spread. Albert Einstein published a paper on Brownian motion, the erratic dancing of pollen grains in water. Einstein mathematically proved that this dance was caused by trillions of invisible water molecules slamming into the pollen. This was the first empirical evidence that atoms weren't just a convenient math trick. They were physical objects. Once we knew atoms existed, we realized they weren't the solid billiard balls Democritus imagined. Rutherford discovered the nucleus, showing the atom is mostly empty space. Bohr realized electrons live in specific energy levels, the solar system model. Schrödinger and Heisenberg replaced orbits with probability clouds. In the quantum world, an atom isn't a tiny speck. It's a wave of existence that only settles into a particle when we measure it. But as our thinking atoms probed deeper, we discovered something terrifying and wonderful. The universe is not merely stranger than we imagine. It is stranger than we can imagine. Our human intuition, evolved to hunt and gather on the African savanna, is completely unprepared for the true nature of reality. Einstein showed us that space and time are not separate. They are a flexible fabric called spacetime. Mass bends this fabric, creating what we feel as gravity. Even more shockingly, time is relative. The faster you move through space, the slower you move through time. If you were to ride a beam of light, time would stop entirely. To a photon, the moment it is emitted from a star and the moment it hits your eye millions of years later happen instantaneously. If the macro world of stars is bendy, the micro world of atoms is chaotic. In the quantum realm, the concept of a clock breaks down entirely. In sufficiently small pockets of space, the Planck scale, time as we know it may not even exist. Quantum entanglement is the phenomenon that famously perplexed Albert Einstein. Two particles can become linked so that changing the state of one instantly affects the other, even if they are on opposite sides of the universe. What Einstein called spooky action at a distance defies our understanding of separation. It suggests that at a fundamental level, everything might be connected in a way we cannot see. Perhaps most dizzying is the many worlds interpretation of quantum mechanics. It suggests that every time a quantum event has multiple possible outcomes, all of them happen. In one universe, the radioactive atom decays. In another, it doesn't. This implies an infinite branching of realities, where every possible version of history plays out. This leads to the ultimate haunting question. Do we have free will? If our brains are made of atoms and atoms obey the laws of physics, is choice just an illusion? If the universe is deterministic, cause and effect, your next thought is just the result of the previous state of your atoms, like a row of falling dominoes. If the universe is probabilistic, quantum randomness, your thoughts are just the roll of a die. Neither option leaves much room for a you in the driver's seat. And yet, the illusion of choice is so persistent, so vivid, that we build civilizations upon it. The story of how we arrived at a place where we can even ask these questions is a narrative of escalating complexity. It began in the hearts of ancient dying stars. Every atom of iron in your blood and calcium in your bones was forged in a stellar furnace that exploded billions of years ago. When our solar system formed, it was merely a chaotic cloud of gas and dust. Through the violent elegance of gravity and accretion, the Earth coalesced. It was a hellscape of molten rock bombarded by meteors. Yet, as the planet cooled, chemistry began to flirt with biology. Then began the subtly simple yet profoundly sophisticated process: evolution. It requires no conscious designer, only three fundamental ingredients: replication, variation, and selection. This simple yet ingenious process is driven by an underlying genetic algorithm, a set of biological code that controls the development and behavior of living vehicles, just as a program dictates the functions of a computer. Operating over billions of years, this automated instruction set culminated in the human brain, a masterpiece of biological engineering that billions of those same brains working collectively have yet to surpass. However, we are entering a new era. Through genetic modification, we are beginning to refine our own species, adding capabilities that nature alone never provided. By fusing this biological enhancement with the power of artificial intelligence, we may soon achieve heights that are, by today's standards, truly unimaginable. In 1859, Darwin provided the mechanism for how species change over time: natural selection. His big idea was that individuals with traits better suited to their environment are more likely to survive and reproduce. He connected all living things to a common ancestor, though he famously didn't know how traits were actually passed down. He thought it was through gemmules in the blood, close, but no cigar. Darwin didn't just suggest we were related to animals. He fundamentally dissolved the boundary between humanity and nature. The paradigm shift. Before 1859, humans were viewed as a special creation, existing outside the laws of biology. Darwin showed that we are not the audience of the natural world, but a character within it. He demonstrated that the difference between a human and another mammal is one of degree, not of kind. Our emotions, our skeletal structures, and our behaviors are simply variations on themes found throughout the animal kingdom. Recognizing that we are a part of nature rather than masters of it changes how we approach everything from medicine to ecology. We study fruit flies and mice because our cellular machinery is nearly identical. We understand that damaging the environment isn't just hurting something out there. It is an act of self-harm, as we are deeply embedded in those biological systems. While Darwin was looking at the big picture, Mendel, an Austrian monk, was looking at pea plants. Darwin's theory of natural selection was brilliant, but it had a massive, gaping hole in its center that nearly brought the whole thing down. He knew that traits were passed from parents to offspring, but he had no idea how. Without Mendel's engine, Darwin's theory faced a fatal logical flaw called the blending problem. In Darwin's time, the prevailing theory was that inheritance worked like mixing paint. If a black cat and a white cat had kittens, they would all be gray. If traits blend, then any new advantageous mutation would be diluted out of existence within a few generations. If a super-fast deer is born, but it mates with a normal deer, the offspring would be only semi-fast. Their offspring would be slightly fast, and eventually the advantage would vanish into the average population. The result: natural selection would have nothing to grip onto because variation would constantly disappear. Mendel's work with pea plants proved that inheritance isn't like mixing paint. It's like shuffling a deck of cards. Mendel showed that traits are passed down as particles, genes that do not blend. A pea plant is either tall or short. It doesn't become a medium-sized blend. He also showed that a trait can hide, recessive, for a generation and then reappear later, fully intact. This meant that a new advantageous mutation could stay in the gene pool indefinitely without being diluted. It provided the permanent, stable variation that Darwin's natural selection required to work. Darwin had the car, natural selection, but Mendel had the fuel, genetics. However, the two never met. Darwin had a copy of a book referencing Mendel's work in his library, but the pages remained uncut. He never read it. It wasn't until the 1930s and 40s that scientists finally combined them in what is called the modern synthesis. This unified theory explains mutations create new genetic particles. Mendelian inheritance preserves those particles. Natural selection decides which particles are most successful. Refining survival vehicles by mistakes in genetic code, mutations, ties back to the concept of entropy. Evolution is the process by which nature sculpts order out of chaos. Mutation is the disorder, the random noise. Natural selection is the filter that keeps only the rare functional order. We are sensitive to order because we are the order. Highly complex, extremely fragile exceptions to the universal rule of decay. How astonishing is the fact that over eons, this blind process of evolution sculpted single-celled organisms into the vast, vibrant tapestry of life. It is a slow, grinding crescendo of complexity. From the soup of the primordial oceans rose creatures that could sense light, then creatures that could crawl, then creatures that could feel, and finally, creatures that could wonder. Conclusion. The culmination of this chemical journey is the human brain, containing roughly 86 billion neurons connected by trillions of synapses. This biological machine allows the atoms within it to look back at the stars from which they came and calculate their age. It is a recursive miracle. Hydrogen atoms, given 13.8 billion years, have transformed into distinct entities capable of understanding the physics of itself. We exist as a statistical impossibility, conscious stardust walking a tightrope of habitability through a silent, freezing void. Yet we are victims of our own efficiency. Our brains, finely tuned by eons of survival, filter out the cosmic signal to focus on the noise. We fall asleep to the laws that bend time and space because we are too busy navigating the laws of the office. We treat the miracle as a given and the mundane as an emergency. Despite living inside this miracle, floating in a multiverse of infinite possibility made of ancient stardust, governed by laws that bend time and space, many of us walk through life entirely asleep to it. We get lost in the friction of the mundane, traffic jams, office politics, and the price of groceries. It is a tragedy that the feeling of awe is often reserved for rare moments rather than being our default state. To look at a tree and understand it not just as wood, but as a biological machine turning sunlight into sugar. To look at another person and see a galaxy of experiences and biological machinery. This should be enough to keep us in a perpetual state of reverence. We are the lucky winners of the ultimate cosmic lottery. The sheer probability of your specific atoms arranging themselves into you in this specific sliver of time on this blue marble is vanishingly small. This improbability is often highlighted through the concept of the fine-tuning of the universe. which refers to all the cosmic constants required for the existence of the universe and the formation of life. However, this cosmic rarity does not necessitate a miracle. We can explain it, for instance, through the multiverse theory, which is not a mere guess intended to avoid the concept of God. Instead, the multiverse is a mathematical consequence of inflationary theory and quantum mechanics. The God hypothesis, by contrast, is an answer that stops all further inquiry. It relegates the question of our origin to the darkness of obscurity, because a miracle is, by definition, beyond empirical experimentation. To be an arrangement of atoms that can think, love, and discover is a fleeting privilege. We are the unlikely survivors of a 4-billion-year evolutionary carnage. Every one of your ancestors, from the first self-replicating molecule to the small, shivering mammals hiding in burrows while the sky fell on the dinosaurs, was a winner. They survived the great die-offs so you could exist. We owe it to the universe and to the billions of years of chaotic trial and error that forged us, to be curious, to be excited, and to never stop marveling at the fact that we are here at all. We owe the universe our attention because we are the only part of it that can pay it. To stay curious is not just a hobby, it is the interest we pay on the debt of existing. So let's wonder,